All right. So we are live for part seven. I'm going to call it part seven of the Synacor challenge. So a couple nights ago, we took a little detour to explore different ways to represent arguments um, and instructions, but I reset the repo to a state before that with a little bit of cleanup added on. Um, Bob Null, thank you for waiting around and prompting me. And let me see. While everyone's getting in here, I think I'll just start looking at our to-do lists. So, Zeno, hello. Welcome, welcome. Always good to have you. Um, so on our to-do list, well, where'd we leave off? So the last progress we made with part 6 was adding the ability to log these instructions and and print them back out, right? So we've got a nice way of printing them. I guess it's a new line here that we could change, but that's a little cosmetic. Um, but currently, when our emulator runs, we can set a state and log all the instructions as strings. What I actually like to do is log these as actual instruction objects. Um, and I've experimented around a little bit with that while I was offline, and I think I have a way that will work. I think I was just trying to be too clever last time with the types, and I think we just model out the instructions properly. We won't have a terrible time. Um, Basically, what's going to happen is I'm going to take the spec and copy paste it into a source file, and then turn the spec into actual source code. Um, and I think that will work out nicely. WFM Macaw, hello. Um, so I think without further ado, yeah, we're going to model that, disassemble it to something readable so we can do some reverse engineering. And my goal is to be able to take, for tonight, is to be able to take my worksheet and in here, just mess around with the emulator, right? So like is, um, this here's icing, right? This is for fun. I mean, it is useful, um, but not for actually digging through things. So I want to play with it, not in the terminal, um, but here in the worksheet where I have a VM and I'm able to filter commands that are running that were calls. I'm going to be particularly interested in finding all of the call instruction locations. Um, yes, state is not necessarily membritic. Okay, before we do that, I could go through a couple of the changes I did to make life nicer. Um, so here's a good example. We go into main, right? And we have a method here for getting and setting R1. I finished these up. They were a little bit hacky when I first made them. So I go to the emulator and I set this register. So the way I do the set register is by calling modify state here, and that takes a state to another state. Um, so in the function I passed to it was modify registers. So modify state itself has a method called modify registers, um, and that takes a registers to a registers, right? And this function I called in there was updated. And that is in registers. It takes a register and a word and updates right at that position. And I wanted to point this out because this is basically a lens, secretly a lens. Um, and what a lens does is it creates all these modify methods for you and wires them. So it does, and it's able to generate those at compile time using type magic. So all lenses kind of follow like a similar path. You might be familiar in Haskell or other functional languages. Um, but what I'm writing here by hand is a code that would be generated by a lens. So that's a little bit more principled. Excuse me. I added one little nice thing here. So all these modify registers, they all modify all these methods here modify stack memory PC. And these kind of conflict. So our state has all these state transitions. Bad cop, hello, good to see you. Our state has all these state transitions, but these are supposed to be like lawful state transitions, right? So when we output, we can only output if we have moved a program counter, right? And that moves us to a ready state. So these are all like state transition methods, and these are what we use to construct or to implement our actual methods here, right? When we're implementing a tick. I don't want to accidentally use these because these are not lawful. So these are for us like hacking with things. So I had them need this emulator hack perm. So in the actual emulator, um, so it does some hacking here. It does some like modification of state, or it does a set register, right? But in order to even call this function modify registers, it needs to have that hack perm. So that's what this import here is at the top, is me giving myself permission to mess around with the state in an unlawful way. That way, my lawful state transitions stay separate from my you know powerful modification methods, right? So I mean, not necessary here. It is a little gratuitous, but if this were a bigger project, that'd be nice to have. So you're somehow watching a VOD, as in like you thought you were watching me. Oh, you did liquid. You did the liquid cake puzzle. Nice, nice. I want to do those soon. Um, and Bad Cop, if you do Synacor, I'd love to see that. I had fun watching Dave Eddy yesterday. I was speaking at 2x in the VOD. Okay. Well, I was just going over some niceties I was adding. So it is nothing necessary for tonight. Um, but for tonight, I want to test out what I'm going to do in a new file here. So we're gonna model an instruction fully, properly, right? So right now we just interpret instructions ad hoc, and we either interpret them into state transitions or we interpret them into these. But like we're not actually saving the structure between printing or doing state transitions. Yeah, welcome. Oh, you missed Scala. What language are you working in now? Yeah. So um, let's make an instruction. Package Synacor. Now, I'm gonna make a little model of what I'd like these to look like. So let's turn off Copilot here. Okay, so for example, let's say I have case class add, and what I'd want to do here is add takes a register to which you're storing. Uh, it's the A parameters, right? So there's A, which is a register, and then there's B, which is an argument of literal. So I say argument of literal rather than just literal because this could be a register reference that contains a literal, or it could be an actual raw literal. So I'm going to model that in here properly. And C is also going to be an arg of literal. Something like that. And then of course it has an associated opcode. So I'm going to have something like trait inst with an opcode, and this extends that trait. So extends instruction with opcode dot add. Right, so that's the code that we want to make work, and this is code that looks much like the spec, and I'm just hoping to translate essentially with a copy paste. I don't know, maybe yeah, right. So here's the name of the instruction, or let's go to add. Here's the name of the instruction. Here's the opcode, which is right there. And there are the three parameters A, B, C. Now the Arch spec doesn't give us the types, but we're inferring that, right? So stores into A, so A is a register, the bitwise, and oh, this is not add, but same idea of B and C. And in fact, I think I'll also just copy these in as dot comments into there. We can do like a big multi-line cursor thing to make that all happen at once. You're in PHP for work, but mostly SQL. Well, if you ever need help looking for a Scala gig, I'm happy to help out with that. Oh, so for this, we're going to need to import our numbers. Import numbers. And let's make this arg. So we have an enum arg. It has two cases. So we have a constant with a value. So arg has a type, right? And that type needs to be AU15, or it could be a word. Let's make it a word. And it also has a ref. And the ref has a register. So value is of type T. All right. And to make this work, actually, no, let's just leave the type there. Make this and then we need our opcodes. Unused explicit parameter. Yes, it's unused for now. Sealed trait. I'll make that sealed trait. Now an argument, the raw argument is just a word. So we need to get a way to get an arg from a word. So object arg, we'll put the static methods here. Def from word. Arg, whatever that T is. Triple question mark. And I guess this T needs to be a subtype of word. Val, we'll make that a val. There we go, that should go away. And we'll need to be able to get the value of an arg. So def value is going to be this match, and we have two cases here. So if it's a constant, we can just return the value that's inside of there. If it's a register reference, well, in this case, we do need to have registers. So we'll use registers. And then that just has an apply method for reg, and that gives us a word. And then this word, well, let's see, value should return type T. So when we get from the registers, all we know that's a word. We need permission to cast that. So we'll get like cast, which is a permission to cast to T, whatever T is. So I'm going to give ourselves a type class for that real quick. So we have trait cast and def apply to a word, and we get our type T that the cast is of. I think that should work. And then object cast. We'll make some casts that are legal here inside of an arg. So we can do given cast of let's say lit. And this is just going to be given cast. We need to give it a definition. So it's def apply w word equals w.lit. Declaration of instance cast not allowed here. Only classes can have declared but undefined. Well, this isn't just a declared method. We could do with. Okay, yeah. We have to use the with syntax. I thought I'd switch to Scala 3.7. We are still on 3.5.2. That makes me worry a little bit because I thought I'd changed it. Oh, right. Let's just do a get restore build.sbt. Okay, yeah. So this syntax here with the colon should actually work. We do need to re-import the build file. Broden White, you're learning to make video games right now. Cool. Well, in this case, we aren't making a video game, but we are reverse engineering one. So maybe we'll learn a little bit about how this video game is made in the process. So this gives us a word, and then we need to cast it. So we cast regs.apply reg. Okay. And then we can make implementations for the other two. So given cast address, def apply w word equals w dot address. And then we have this from word. So I think this would basically be, we have something like this in our VM state. It's U15. Okay, here one we're dereferencing. Yeah, let's basically copy that. So from word, we need the actual word parameter to an arg of type T. So if it fits U15, we can just wrap it. So we can do arg.const of W, but it needs to be an arg of type T, so we need also cast. So T is a subtype of word and has a cast. So now we can do cast here. Though we do also need a cast method. So def cast T of type T gives us a T. Or no, we have a word. We have a word and using cast. So we need a cast for T, and then we can just do cast.apply to that word to get the T. Okay, now I should be able to call this cast function. Because we should have a cast in scope. Not found cast. Oh, right. Well, actually, we want it applicable more generally. So let's make this an extension method on word. So extension w word def cast equals cast.apply. And cast here has a type parameter. Okay, so what this is actually going to be is w.cast. Otherwise, we create a regref, so arg.ref to w.register. Cast is not a member of words, but be made available as an extension method. Right, I guess we have to import cast.cast. There are many different ways to skin this cat, but we found one way. Okay. So I think we have like all the mechanisms in place. We do also want to, so we have a value method, right? So we're able to extract the value once we're actually implementing these state transitions. Um, so I want to just give ourselves a test of that. So something like def tick. Let's make this an extension. Extension on VM. So we have a ready VM state. And if we do a tick, then we want to do like a VM.instruction. So instruction VM.inst, I would like it to give us our current instruction. We don't actually have that yet. We have the current opcode. Uh, so let's do that first. What does that look like? Well, I'm going to implement it in here. So we have this tick function. Let's now add a instruction function. So def inst, and then we're going to match the opcode. So opcode match. And right now we only have one that we're making. So if we have add, then we're going to get the add instruction. And actually, I want to put these inside. We'll put add inside of instruction by doing object inst. And now we can say a.reg. B, we need a way to get the arg. So we have this from word method already. Let's see. We have extensions on word. We can do something similar. So extension w word. We have a literal arg and we have an address arg. That's only two ways I ever use. So let's say lit arg gives us an arg of lit. And that would be arg.from word, well, w. So now we could do something like b.lit arg, and we can change the name. I'm hoping I can get rid of other things and maybe be able to just say, well, I'm not sure. I could have a method called just arg where I pass in a type parameter. So instead add b.lit arg, c.lit arg. Inst.add is not in there. It should be in here. I think the compiler is just catching up with us. But yeah, so that's what that would look like. And then when we're actually doing the state transition, let's just make sure we know what this looks like here. So we'll match. And in the case of add, now this add instruction, is going to come with its parameters. So A, B, and C. And now we can do, let's go find our previous add. Something much like that. So it would be, in this case, vm.store a.reg, and then b.value plus c.value. Yeah, actually that code doesn't change at all. Well, no, A is already a register, right? That's a parameter here. So we say A and then b.value, c.value. What are you missing here? Oh, we need an equal. So tick returns a tick. That's implemented by that. Okay, that's a little bit more sane. Oh, instance of type registers. Oh, so for that to work, we would need to do like a given VM dot registers. Registers is not a member of VM state. It absolutely should be a value of it, right? I mean, I can just jump to definition, no? So case class VM state, it does have registers. Did I misspell it? All right, well, I'm not sure about that, but it looks like this general idea will work. So let's go into the work of translating all of our instructions into this. And how can we do this? So what I'm going to do is I'm going to copy all of these cases and do a big multi-line edit. I think that will be very satisfying. Or I could do it from here. I want one line per. Do I have them listed anywhere? Here. Okay, these are all of them listed in order. And you know what? These actually could be enums. So let's make this, instead of a sealed trait, we'll make this an enum. And then instead of a case class, we just have a case of an enum. Yeah, that should work. Okay, so all of these cases here, comma, separate those lists. And I suppose I'm doing this. Oh, I could have done that with a multi-line, but there are only a handful of them. Okay. Great. So now this we turn into whoops. I was hoping to delete just there we go. Delete all the spaces. So these are all going to be cases here. Case, and they're going to look like that add. So they're going to have some set of parameters. In fact, I might just add all of those in. No, I think there's no need. So they'll have some set of parameters, and they'll have dot extends inst with opcode dot its own name. Because the opcodes are named exactly like the instructions. Okay, there's the basic framework. Now for all our binary instructions, we have A, which is a register, B, which is an arg of type lit, and then we have C, which is also an arg of type lit. Okay. Greater than, equal to, I think are also binary operations. Yeah, it's the same thing there. Yeah, greater than, equal to. I'm going to pull up my living spec here in VM state. So greater than, B and C both have values, and then we store an A. Yep. So A is register, B is an arg of type lit, and C is an arg of type lit. Jump true and jump false. In both those cases, A is an address. No. A is a value. So A is an arg of type lit, and then B is going to be an arg for an address. Jump just has an address. A is an arg of address. Pop, I believe, has no args. No, it has a register to which to store. So A is a register. Push, we push a value, a dot value. I'm not sure what the value is. I'm going to say lit for now. And if we're wrong about that, the type system will tell us eventually. So let's say this is an arg of type lit, and then B, no, A is a register, no, push. Oh, there's no other argument, right? Because we're pushing to a stack. Wait, how about the pop? Why is there a pop? Right, we pop it and then we store it into the register. Okay. Halt actually just has no params. Set a register and a value. A is a register, and B is an arg of type. Not sure. I'm gonna say lit, and also I think I can kind of say it doesn't matter because I don't know, if we parse it as a lit, it's the same as parsing it like an address. So that could be like U15 for all we care. Yeah, in fact, I'm just gonna say that along with push. We'll say they're U15s. It doesn't matter that we don't have cast instances for them because we're not pulling them out. Those are input arguments, and we're not doing anything with them. Okay, not also has an A register and a B, which is an arg of type lit. Okay, read mem and write mem. A is a register, B is an address, A is an address, B is a value. Okay. So A is a register, B is an arg of address. And here A is an arg of address, and B is a value. Let's just say that's an arg of U15. And call. Call has A as an address, and that's it. Return. You pop. So return has no arguments. No up has no arguments. Out has no arguments. Well, hold on. Output. You output A. So A is then an arg of U15. Well, no. It's not U15. Let's say lit because out's going to be turned into a character, right? And then in. That has no arguments. No, that's not true. Right, it's doing this. It stores into the A register. A is an arg type address. Great, add is already defined. Yeah, so we don't need that there. Cool. This is too long. Okay. Now the other thing I wanted to do was take all the dot comments from the spec file. So I'm going to do this, add a new line in front of each of those. And then we're going to open the arc spec. No, hold up. Let's open that in the other window. So we'll open that here. Okay, I think what we have to do to make this work, let's add a bunch of space here. Oh no, we don't need to add a space. We just need to grab all of these. Okay. So the way this is working out, it kind of makes me feel like I should have just started. The first thing I should have done was translate my instructions, my spec directly into code. but I don't know. It would have been hard to predict the way I would use them all, so that would have been hard to do. Okay, and now all of these can have doc strings. What is inst and how does it differ or relate from opcode? Good question. So the point of instruction of inst here is to model a full instruction, not just the opcode itself. So it models the arguments of an instruction, as well as the types of those, right? So the example I've been running here with is and. So and has, it has its opcode, but this knows that the a parameter of and is a register, and that the b parameter is a literal, and that the c parameter is a literal, right? Or not that it's a literal, but that it's an arg of literal. So it knows that it could be a register reference to literal or a constant literal, literally. Yeah. So the point of this is that now we have all of this information made explicit, right? We were just using this information implicitly before. Um, yeah, the fact that these all have like A, B, C, etc. I could have almost just taken these lines themselves, a line like or, and that's almost exactly what I translated, right? Except there's no types. So or has an A, B, and a C. And now that's honest in here too. Or has an A, B, and a C, except here I've added types. Okay. So we want a way to get now the current instruction from a running program. So let's implement that over in our VM state. So def instruction. This is sort of essentially another copy paste. Now these args, I think what I wanted to do here, let's just do arg by type. So arg, give it a type. So we can give it a type in if we need, but it should just be inferred. So arg of type t and arg.fromWord. So it has to be t to which we can cast. This fromWord is going to cast down to that. So this we can just do now with, well, hold on. Let's fix all of our type errors. Both given cast lit and given cast address and object cast match the, well, this needs to be a subtype of word for one. Word that has a cast. Right, there we go. Okay, so let's do that. But before that happens, I think we're going to have a cast for U15 because we used U15 in there a bit. You know, to do hack. Okay, that should type check. And now let's see how this looks. So instruction. So we're going to match an opcode. Op match exhaustive. And for each of these, we're just going to use a matching instruction. So this goes to inst dot that name. And then here we go a bit manual again. So set takes a what? A register, not an arg15. Let's see, my autocomplete should help with this. So a.reg and then b.arg. Cool, that works. These red line comments kind of get in the way. It is a weird color for a comment. Okay, so push a.arg pop a.reg equal a.reg b.arg c.arg, where then same thing a.reg b.arg c.arg a.address, or arg rather, it's an arg of address, but that type is inferred. Jump true and jump false, a.arg and then b.address. Mod and or a.register b.arg c.arg. Or was the same thing here. Not is the same thing minus a c. Read mem, write mem. Those are just the same thing in different order. Register arg. Oh. A.register b.arg a.arg b.arg. And this is an arg of so these are arg of an address. Wait, what is this? So these two do both have types, but they are completely inferred. So that is a side effect of that. Like maybe I did want this to be like a.address, because this would be like a.arg and address if you want to be explicit. And I do like having that be explicit in the text so that you can see what type it is while you're reading it. So that's a thought for cleanup later. Call takes an address, a.arg. Return takes nothing. Out takes a literal, an arg, and takes an arg. Oh, yep, arg and arg. Okay, now we can get the instruction. And then now, so this tick, instead of moving from an opcode, we can replace this with inst, and we can match that instruction. And then if we were to do that, we'd have code. So if we look at this code here, starting to write, right? What we had before was something like, was code that looked like this. So we had like opcode.add, and then here we interpret those values. But here, this time, we have inst.add, and now we have those three values already, but those already have their types assigned to them. So we don't have to interpret the type over here when we're messing with them, right? We used to do like A, B, and C were all words. So we'd say A, let's cast to register here, and B will cast to lit, and C will cast to lit, right? We had code like that. But here, we just know now that B is an arg, so we can get the value out of it by doing dot value. Yeah, so let's comment that back out. And these things need their parameter lists. I think the best way to do that We'll comment this out. And we're going to do inst match exhaustive. Okay. And from here, I guess we basically sort of copy that code over, because I wrote it in such a way that the code would look identical, even though it wasn't semantically identical. Okay, yeah, I hope the value of that makes sense. Um, so set right. I do like adding this dot store bit. No, I'll not do that. Um, to do commuter reference A. I think we already kind of answered that question. So this pop match, that should come out the same way. Oops isn't going to replace the, is inst going to, it's not going to replace it because we still have the enum, but inst includes it, right? So an inst has, if you go like to, it's still there. The opcode is still there. But in this case here, it'll replace it because it has more information. So it's like we buffed our opcode enum. Okay, so we have the equal. I do still want that boolean toLit, because then we can just store this dot toLit. All right, Cam. See ya. Have a good one. Thanks for stopping by. Good to meet another Scala dev. Okay, b dot value. No given an instance type Synacor dot registers was found. Right. We need given registers, or I don't know, given registers equals this dot registers. There we go. We found a U15. We required a lit when we got the value out of that. Okay, so that actually, let's go back to our spec. And when I say spec now, I mean this page. So set required a U15, which should actually require a lit. When you push a dot value, yeah, we're doing that with a lit. So when you store, is that right? Should we always just be storing a lit? Well, I mean, it worked in practice when we were running the VM, so I'll just believe it. So this is a lit as well. Probably every place we used U15. Okay, we can fix those later. Okay, so we have equal to, we have greater than coming up right here. Jump. You know what? I'm not gonna make you watch me copy paste. At this point, Copilot should know what I'm planning to do. So I'll have Copilot like autocomplete this. Oh, this is not a.address. This can just be a.arg. Yeah. And autocomplete's not correct, but it's close enough that we can just fix compile errors. those really correct? Okay. And I want to remove all the this calls. There, we can just do that. And then call. That can just be one line. Push and then jump. Yeah, that makes sense. All right. You think inst is like what you did in Rust, like you described. You pasted the arc spec and started defining lopping node inline. Yeah, that's what I should have done to start. You found a bug in your Synacor. Oh yes, I saw you're doing Synacor. It only took reading the bytecode in the hex editor to discover I was parsing it incorrectly. Fair enough. Um, I don't think I've had to do something like that yet because I was upfront with my types. So I think they were compiled errors before they were bugs. Okay, I think that I can be happy with. Now let's work out all of the compile errors. Okay, what do we have here? Arg is not a member of, wait, what is it? No. Sorry, A is an arg, so it's not arg, it's a.value. So we're calling value on an arg. Address should not exist anymore, so it's just dot value. Value. Yeah, it's dot value for all of these. B. U15 required lit, so let's go to WMEM. We're gonna say B is a lit. We're not writing addresses to memory. I mean, maybe we are, but it doesn't need to be distinguished at this level. And here, required a word. You know, I don't think that needs to be true. So a word, well, we're interpreting a word as a character. Mm. Yeah, I guess it makes sense that we would do that with a lit. Because we wouldn't really turn addresses into characters. Okay, we can change this to a lit. So this can be n lit, deref n as car. And I think we can also get rid of this deref. Oh, hold up. You don't deref lits, you deref args. So that's why that was a word. Okay. We go back to our instruction here. So output should take a character. So a.value should give us a character. Or you know what? It should give us a lit. So the dereferencing is already done at this point. So this is an n lit. And then we can just do n.as character. Okay, that makes sense. Cool. You would have done the better test, but you didn't know how to write, save, raw binary files at the same time. Fair enough. Although you don't I guess it doesn't need to be raw binary, does it? I don't do raw binary except when I'm parsing it in. And I suppose I would make my test cases just by hand inside my model here. Um, does everything work? I think everything works. No. It can't just work. We have compiler errors still. So inst, we have apply. Let's go back to inst. What's going on here? We're not seeing compile errors. Oh, hold up. You have to reload. Reload, compile. But the next bit, so the goal here is to use this in the worksheet, right? So we're already a little bit better off, and now we have a proper model, but we should actually use that. So the only way we're using it right now, well, we're doing this show, and this is still doing it based on ops. Now, here's part of the reason that in the instruction I modeled them not as like the literal that's being added, but the argument that could either be a reg reference or a constant. Because here is one case in show where how you print it depends on whether it is a reg reference or not. So I think I do still want to do that. Let's make a show method for inst. And we could have that be, so show string this match. And no, I don't like that. Oh, wait, it kind of knew what I wanted. Yeah. Although, huh. Um, but arg itself needs a show. And I'm not interested. It needs a show rather than toString because how arg is printed is contextual. It depends on the value of the registers at the time the arg is printed. So we'll need a show method for that before we can do this. So def show string equals this match. And in this case, constant, it is value.hex. Or you know what, we're going to do a value.show. The addresses, I want to show them, I think I want to show them differently. We can do that for now. So this is going to be much like we had in this implementation here, show arg. We had the reg name. So reg.name, oh, no, that's exactly it. And then the parens. And then the dot hex of that. But in order to get that, we need registers. So using registers. Okay. So a show for instruction then also needs registers. Def show. Who needs tests when Synacor has its own self-tests? Yeah, that's fair. That definitely makes it a lot easier, doesn't it? It does make the challenge. It is very nice that it's there. You saw your model kept the high and low separate. You merged them. My handwritten test is only for 16-bit and it's not for the 8-bit bytes. Oh, okay. That's fair. Yeah. Yeah, for a second I was separating Right, that's how I implemented it at first, right? I had um, a num with a high and a low, and that was silly. I just parse it into an int now. So I parse it directly into an int, and I just do swap from little to big endian when I parse it, and from there I don't have to think about it again. And I saw Dave Eddy ran into the same thing where he'd had bugs because he was playing with them swapped and had to remember that they're swapped. Yeah, I think it's better just to, if I'm ever writing to file, I'll switch it back to little endian. But the only time I worry about little endian now is when I'm parsing it. Your self test is an infinite loop because it's jumping to the wrong address. Fair, right? You have to have some amount of accuracy for the self test to run. I mean, I never got to see the self tests failing. The only thing I ever got to see it do was stall because I'd forgotten to call progress. So I didn't know that would like help you along using registers, right? So it's gonna be this match and oh, the second one is match with okay. Yes, yeah, that works. Okay, Copilot, you did it. Okay. There's one thing I want to do differently here though. I realized that my output was a little bit confusing when I was reading through it. This read mem and write mem, a.name, b.show. So b here is an address, right? But what we actually do in the implementation of read and write mem, where is that? So in read mem, we read the value at that address and then we store it. So I want it to be clear that we're not storing that address literally. We were first dereferencing it. So I'm going to do something like this. To show that it is reading an address. Whereas for jump, this is an address. This a.show, that's an address. But in this case, this address is actually just a value, right? That value is being used. I mean, this could be a register, right? So this could be like r8 parentheses and then raw address. But that address is not being dereferenced. Well, these two addresses are being dereferenced. So I'm putting those square braces to distinguish them. Same with call. No, call, you're just jumping to that address. Yeah. But in these two cases, you're writing, yeah, okay. And I think it's only those two cases. If anyone can think of anything else, that's a kind of backseating I like. We do need show instances though for lit. Is it fine just to do hex? I'm not gonna write addresses differently from literals, am I? I think I don't need to write addresses differently from literals. So we'll do that. And now in our VM state, we can remove this show implementation and we can do just int.show using registers, right? And where's the other place we use registers? Right down here. Okay, so now we've done this in separate steps. Instruction parses our arguments and gives them types. And then tick now takes those parse instructions and does the state transitions. And show, where was show? I think we want to move show lower. Oh wait, show is just one liner now. Show defers to inst. Where again we use those parsed instructions. And then now another thing I like about this is that based on the type of C, we can call a different show, right? So all these arglets, before when I was writing my show function, I had to say like show this as an arglet, which means dereference it or try to dereference it. And if you can dereference it, just show the raw value, or well, show the raw value, but also show the register name from which it came, you know? And I had to write that explicitly. Now in this case, I could write it generically and just write show. In fact, this could probably be even more generic since this is a case class. The case classes are actually kind of linked lists. So there's a tuple, right? And that tuple has a type. This tuple has a type. This tuple is type int. So you can cons them like a list. So the type of that is int. You can cons that onto something else. So this is three things cons together. And you can break down any case class this way by taking like its tuple of types and writing a recursive function that handles it based on those types. So I could actually write a function that does this generically for any int, just takes all of its arguments and then inserts a space between each of them or something. Now the show isn't exactly what I wanted. Well, actually, I think it's fine. But in the VM state show, def show, I think I also want, well, I know I also want the address. So at pc.hex, pc.hex, colon, and then let me show that instruction. Okay, so let's see how that looks. Oh, let me catch up with you. So Bob, no, you implemented toString stuff and realized the way I had structured this thing meant you couldn't print the dereference register value. Yeah. Right, like so my instruction has a built-in toString, right? You can print any case class, but it's not going to dereference it unless you have where's my show method? Like I have my show method, I have to have a contextual register. Sparkly, you're enjoying doing it one bit at a time, so you're seeing that the self-test is actually testing stuff, not pretending. Ollie wants it really is admonishing me for opcodes you haven't done yet. Yeah, I'm kind of sad I missed that. Eric was in chat here saying, hey, you know, you can just run it. And I was like, no, let me just finish them all first. But yeah. Yeah, I agree. Incremental progress is nice. Okay, we've got a lot of other warnings here that shouldn't show up again. Right, so I just switched the Scala version, updated it, so it's recompiling. It's giving me warnings. Okay. So let's uplog toggle. So now it's on. And then we are going to use teleporter. And we're gonna uplog show. All right, and I just noticed something. Let's go to build.sbt because in here somewhere we have lost. We lost an option. Standard out something. Actually, I think it is in my git stash apply. No, no. Wait. What was on my stash list? Shit, I don't know what I applied. Let's just get stash show or list. And then we'll show this one. Get stash show B. Okay, output strategy. Right, we need this in there. After connect input. There we go. We need that to get like the little typewriter effect. Cosmetic, but yeah, and this is what our thing looks like now. So greater than R1, R4. That's printing how I'd like it to. But now the difference here is that these are all parsed, which means we can play with them in the worksheet. And I've added this little difference now, right? So now we know that this is a memory location that's being dereferenced. So we're not reading or writing like this. We are first looking to memory. Or in this case, we are writing to the memory stored in R4. This is the address that's stored in R4. I kind of want WMEM to show me the value that is being written because it gives me an address, and that's why it show. Let's see, do we have a WMEM in here? WMEM. Right, in this case, we are writing to this address. Oh, I guess that's fine. We don't need to know what was in there. I guess in the case of RMM, we might want to know what we're reading from there. So I'd like to know what value you're reading from this. And I could easily do that by adding in memory. Let's do that. Why not? So inst.scala using registers and memory. So in the case where we read from mem, how do we show this? So in the memory there, we could do more parens. More parens, and we do let's see, summon memory dot apply the address, and that would be b dot value. Yeah. And if you go to VM state, that should be failing now. So using registers and memory. Okay, let's try that again. Oh, hold on. Nope, let's not start that. I'm just gonna reload. We want that new setting in so it has a typewriter effect. I may discover the other self-tests depending on how you unravel the rest of the binary. Wait, really? There are more self-tests? I mean, I'm already past the self-tests, right? So uplog toggle. You're saying there are like tests afterwards. Use teleporter. But that's impossible. There are no bugs, so there's no way I can see them. I have too much hubris. Cool. Yeah, now we're reading mem. And we know what values we're writing. Oh, wait. That is a raw value. I think we want the hex version of that. So in inst.show, we want the hex value of that. b.value.hex. Okay. And that is fine. Now let's look at our WMEM. I just wanted to double check that. The self-test I might have missed. Oh, you mean, yeah, if I screw something up. So when we write to mem, we are writing to this address the value in register 4, which is A. Okay, yeah. Cool. I think that's helpful. All right, now it's time. Now it's time to really look at the bytecode. This is the moment I've been kind of stalling on since the end of part 6. So I appreciate y'all coming along with me for this little digression. I think it's worthwhile. We're allowed to have fun here. Let's go to the wait. Our op log is still a queue of strings. We do still need to change that. And then after we change that, we can play with it in the worksheet. Oh, right there. I had this bit of duplicated code. I think we'll change that while we're at it. I think actually I want to keep the string along with the instruction because the string has information that the instruction itself doesn't have. So let's make the op log a queue of inst and its string name. Okay. So ops and queue, we do state.inst and state.show. Right. That's not a good name anymore. I think that should be show inst. Or, yeah, I'll just make it show inst. State.inst, state.show inst. What's going on here? We need to make that a tuple. This needs to be an instance string. This needs to be an instance string. Now we in queue required an inst. Hold on, ops. What is ops? No, it's a queue of instance string. It's right here. Too many type arguments. Oh, wait, we need parens because it's a tuple. Okay, and same thing here with progress until blocked. Instance string. Inst and string. And then when we enqueue it, we do state.inst and state.show inst. State.inst and state.show inst. There we go. I still want to clean all this if else stuff up. But you know what? Let's do this. Val log equals. So it's either going to be if enabled, if oplog enabled, then we give just this bit. Yeah, else ops. Okay, I think that's what Copilot is trying to tell me. And then we can just put in the log here. Okay, I think that works. Let's see if we can get Copilot to do a similar factor here. Val log equals if yep, we got exactly what I wanted. Nice. And now there's a subtle difference here. We have chars and q in this case. Let's see if Copilot catches that. No. Val log equals ops and q else ops loop state.take chars and q. Alrighty. Great. Now when we get, let's see, in main, when we're printing this, oplog show. You know, it's not the worst thing to print it that way. No, we're gonna do map. Well, actually, I just want to see what it looks like. So we'll just swap the order for now. And instead we can take the first. Like, what's going on here? And where's our main? I think we want to skip the shortcut. Yeah, we'll skip the shortcut and we'll do val emu.up. No, we'll do emu. It's emu.toggle. Toggle oplog. Okay. So we're running from the beginning. So we can just open it up and show the ops right away. Okay, now we can go to the play worksheet. Okay, so we have a start VM. What's wrong with this? Show instance not a member? Interesting, because I thought we just defined it. Yeah, it's right here. So I think our worksheet is just lying to us. I don't know. But let's make sure this is case RMM. Oh, we're not even compiling. What did we change here? It found string required an address. Where, really? Inst Scala 999. This is in the show method. So memory.apply. Oh, apply the address, b.value. Right, and that gets us a value out of memory. And then that thing we convert to hex. Okay, cool. And maybe now this will compile in the worksheet. There we go. Okay, so now that should be printing something. Okay, cool. We're able to show those instructions. Our emulator. We want to progress multiple, so we're going to do much like what we do in main and go to the teleporter. So main we'll take that shortcut. Whoops. Feed multiple, progress until blocked. And then we don't need that look. We do want to get rid of the output. Okay, cool. Now we can do emu equals emu.toggle oplog. We can check on emu.oplog. Enabled rather. So at this point it should be true. And then we can check the size. Oh no, we need to do transition. So emu equals emu.feed. We're not going to look. We're going to use teleporter. This is the moment indeed. And then we're going to progress until blocked. Actually, we could just do that in line here. So we're going to progress until blocked. And let's use the output so that we're not doing anything with it. Or, you know, we can do a print line. Why not? Print line. And then from here, we can look at the oplog size. 11,000 instructions ran. And I think in this line, we should be able to see, oh, we don't see anything. Well, that's fine. So now emu.oplog. So for each of these, we just want the instructions. So map 1 to get the instructions. And let's start with the for each print line. Okay, so now here you see the instructions printing without things being dereferenced. Oh, I think that's a register. Yeah, like the register doesn't have a toString even. I think I should give register a toString. That looks nice. But now we can do things like this. Let's count how many are calls. So .map1, and then let's do count. .op equals opcode.call. How did it know? And then we can do a filter, 964. Filter for each print line. Take a look at that. Okay, here are all my calls. They are all calls to addresses or calls to an address in a register. Cool. Great. I think we also want to see what's most common. So we can do a counts. So val call counts. So we're going to do group map reduce. I don't think we need show. No, just group by identity. Yeah, there we go. And excellent. Sort them and print each line. So now we can see what the most common call is. Okay. So 638 times we have this call. Now, I think I also want the address where that happened. I think I want the... Okay, this is useful. This is a good start. Now we're starting to actually find a place where we might be interested in removing code. So once we get the address where that call is happening, well, okay. No, the most common thing is to call into whatever's in the register. So that's going to be calling many different things depending on what's in the register. So the one we're interested in is that second line then, 266, because that's a constant address. So we need to look into the binary at that address, at that second address, 2125. So I'll write that down, 2125 dot address. And there's the function I want to take a look at. Okay, I'm going to take a bathroom break and be right back. Alrighty. Um, this address we're interested in because it's the second most common call. So let's look at the memory at that address. So let's take emu dot state dot. Oh well, can't necessarily do that, can we? You know, let's just look at the raw VM state. So VM, so start VM dot memory. And I think we want the instruction at that address. So let's do this. Start VM. Oh, I get to try my hack. So given emulator dot hack perm. Now we're gonna take our start VM and we're gonna update. So dot modify PC. Just gonna be 2125 dot address, and we show that instruction. Okay, Copilot is helping a little bit too much here. 2125 dot to address. Non-member of. Wait, I don't have that. So we're address dot from int. There we go. What's going on here? Oh, we can't do that. So that's the thing that's being called. We're going to the address. So I think we want to keep taking from that memory. So start VM dot memory, and then we want to get a whole range of memory, don't we? So this will just show us like a push command, a push op. Right, that is what is there. Yeah, I think we want to parse instructions. So given a memory and a start address, so def extract function, function, there we go. Add an address. Let's make this an extension on memory, on VM state rather. Okay, add an address. So we've jumped to this location, and now we want everything until a return. Unless there are other calls, in which case, how do we know we've returned back? Oh, no, there would only ever be one return. Right. If we have a call, then the return's going to be in some other code altogether. So we can just take until the next return. So we're going to do like some sort of memory dot slice, I suppose. Well, we want to get instruction by instruction, don't we? So it's going to be, yeah, a list of instruction. And let me turn off Copilot for a bit because I want to do this myself. So vm.memory address. I suppose I could construct a list recursively. So def, we have a loop. So we extract until we find a return, basically. So and here's the thing. We'll need to know the number of instructions to jump past. And I had implemented that here in VM state, next instruction, and then progress. So I suppose I could keep progressing that. I need to progress by that amount. I don't think I need to tick through everything because it won't even make sense to tick through everything because the values in the registers might not be any good, right? And when I'm ticking through, what it does actually depends on what values are in the registers. So if there's a branch, it might branch, and we don't like that. But we want to do a raw progress. So we always progress to the next instruction. And for that, we need to get the opcode, and so we can get its number of params. So some of this stuff I want to extract out of there. Oh wait, op.number, yeah. So AHA's op define is just memory at that PC. Okay, so val op equals vm.memory at our address. And then val inst equals, see, how do we get an inst here? Def inst. It depends on the op. But all it needs is A, B, and C. So we need to get a way to get A, B, and C. And now in this case, it doesn't matter what the raw values are. So this is a case where actually we don't want the show version because the show version shows the contextual value. We just want the raw instruction itself. And that's what this is. This is the raw instruction. So if we can extract that or just do the same, I think we need to extract it. So we parse an instruction from an opcode and from 3 potential words, right? So we're going to move our parse function outside. But you want it to look like this: val inst equals inst dot parse, and we define a, b, c, much like it's defined up here. Except it's not PC, it's address. So inst.parse, we give the op and A, B, and C. And the thing is, A, B, and C need to be lazy values because they might not actually exist in memory. Yeah. Because they also may not be required. So here in the lower left or your upper left, I'm going to go to inst and we're going to make a parse function. So we have enum inst. Let's do a companion object. So object inst def parse given an operator and A, B, C. So operator is an opcode. A is a word. B is a word. C is a word. And these are all lazy. So we're going to put that arrow there. And this gives an inst. And then we can just copy over our def inst. How do you want to do this? Put that match up there. Cool. And now all these cases are opcodes. Right. .arg was contextual. Why does it have to be contextual? I don't think it has to be contextual. At least it shouldn't need registers. It doesn't need registers. It just needs to cast. So beta arg. Oh, A is not a member. Sorry, I think I'm doing biname parameters wrong. Is it that way? No. Let's say you do biname parameters. So A. Oh, right. Arg is not a number of words. Yeah, that can be defined here. Inst.arg. That extension words, it makes sense to put it down here. Or, we could just say arg.fromWord. Actually, that's exactly what we're doing here. Okay, so we'll put that here. Okay, now we're parsing that completely independently. And in our VM state up here, we can just say inst equals inst.parse op a, b, c. Okay. And then now back to our worksheet, we can parse here as well. So inst.parse, great. And now based on what this is, we decide to recurse or not. So inst match case. So if there's a return, oh wait, no, match. So if we have inst.turn, then we are done. So we can write a nil, an empty list. Otherwise, we do inst and then we recurse onto loop at the next instruction. So next instruction, we also kind of want this method. I'm kind of deciding where to put that. So we jump based on the number of params and then we increment. I suppose that can be a method on address where you pass an op as a parameter. Let's see. I'm just going to implement it in here in my worksheet, and then we can decide to move it if we like it. And we take that same implementation. So like this would be, I guess, an extension on address. Oops. And let's put it out somewhere else here. Get that out of the way. That's gonna be a library-ish method. I guess both of these methods can be put into like some sort of trait that gives us ways to mess with the VM. We're not even using a VM here at this point. Yeah, all we really need here is a memory. Okay. So now we loop with address.next instruction given our opcode. Okay. So let's try to extract that function. Extract function at what address? 2125. Or each print line. Oh, okay, we need a type for this recursive thing. This is a list. We have an issue with this. Extract function on VM, vm.extract function. Or no, start VM. Start VM.extract function. And hopefully like the memory isn't changed. at the point that this is running. And it is just a stored procedure that isn't overwritten. Found a word, we need an opcode. Oh, right. So how do we do it up here? Def op memory.op, right? Let's do memory. We don't actually need the VM itself, so let's just get as little information as we actually need to do this. So start VM.memory, the extract function, and print that out. No, it's not a member of memory. We just added it right here. Oh, that's still an address. This here is a memory. Okay, dot memory dot extract function. And we can remove these type parameters. And we have an issue here. Found unit required. Oh, we required a list, but this is a list. Loop should be returning a list. Found unit required a list. Does it think we're assigning that somewhere? Oh, right. Hold up. We have to actually call our loop. So loop starting from. Oh, this is where we would actually use the vim. Or no. Starting from. Well, when you extract a function, we need the address, right? So the address. Right. Okay, well, let's give that a second to run. Where's my metals? Hold on, we actually do still have issues here. PC. Next instruction. These are actually all operating on A. Okay, that's all of it. There we go. Now we have our stored procedure. So this one, which ref, okay, those are registers. I think you want the names for those. I'm gonna just change the toString to the name. And then ref, how do those refs have values inside of them? Oh, no. Those refs don't have values inside of them, right? Those are just the ref IDs themselves. Okay. Yeah, I think we need toString methods. So let's look at our numbers. So register, where's it defined? Right, we can't actually override toString on an int. So, geez, I think we have to do a toString on instruction itself. Okay, let's do a toString, def toString, and I'm not gonna do a big match case. Or you know what? Let's do a toString on an arg. So in the case of def toString string equals this match exhaustive. Okay, in the case of const, we just do value dot hex, and in the case of reg, we just do reg dot name. Yeah, I think that'll work better. This will be a little bit more legible. Well, hold on, this hasn't actually implemented yet. Overriding method toString needs to override modifier, of course. I just want this to reload. And here we go. Maybe. All right, push R2, push R3. All right. And not or, and then we pop. When we pop to an address, right? Oh no, that's a register. 32769. I think we want to override the two. The toString of inst. But let's see. We take an inst. So there's an inst. So what can we actually work with? So n dot product element. No. Product element names. Product iterator. Yeah. And then map. Okay, yeah, I think we can do this. So let's go to our enum inst def a toString. So toString. We need an override modifier. Now we take this dot product iterator dot map. And we're mapping over an any. So I think we only care about the case where it's a reg. So case reg. I hope we can actually do that runtime. So reg, dot to, no, reg dot name. There we go. Otherwise, you just do the usual toString and dot toString. And we're going to make string there. We're going to start it off with the name of this thing. So this dot product prefix. That might be it. Yeah, followed by an open paren, and then a comma separated, and then a close paren. And type test cannot be checked at runtime because it refers to an abstract type member or type parameter. Yeah, we can't do that. Not without adding some sort of we could do something clever, I suppose. Like some sort of casting if the T-string matches. Okay, by clever I mean hacky. So reg, if reg.toString .toInt option dot is defined. And then we'll do reg dot as instance of reg dot name. Okay, very hacky, but that should work. Yes. Okay, that looks better. Push R2, push R3, pop R3, pop R2. So whenever this function is called, it gets R2 and R3 out of the way. So R2 and R3 then are they used in all kinds of functions? Let's try doing this extract function for every other function that is potentially interesting. So what are interesting functions? Oh, what happened here? We have hexes now. Here, I'll show you. Or okay, this is nice. So we have hex addresses. So that first one we were looking at was actually 84D. Let's take a look at 5B2. So we'll do the same thing, but for 5B2. 05B2. Yes, hacky indeed. Oh, this is an interesting function. So interestingly, so this function pushes R1, R4, 5, 6, 7. It pushes most of the registers. And it does all this. It calls another function. The function stored at R6. But what is at R6? We know we push R6 to the stack. We set R6 to the value of R2. God, this is convoluted. Okay, this one I think I want to dissect. Yeah, this is a meaty function. Dynamic live assembly? What do you mean? This is the code that's stored in memory at the start. So it is a stored procedure that would be run. And this one is called like 20 times. Let me see. It is called 20 times. So I'm going to drop this into a Scratch file, but before we do, I think I want to comment out. No, we're fine with that. So we're going to copy worksheet output. Or, while we're here, let's just get the next one. 683, that's interesting too. And maybe the one that's called just once. No, I guess there's a lot that's called just once. So let's do 683, since that's called 18 times. Five, 683. And now I just had a realization. And that is that Probably one of these functions is the input parsing function. So if we had, okay, what do we do? We fed this, and then we progress until blocked. I think I maybe want to start the oplog after the feed part, because maybe that's being called, you know? So we could do this. Emu equals emu.progress until blocked, and we can see how many instructions it takes just to read that input. But how many characters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 characters. I didn't see any function that's called 15 times, so I think maybe not. Also, only 11 instructions were run. That is funny. So let's print that. Emu dot oplog. We can just do it for each print line. So these are the 11 instructions that are run after you feed input. Oh, write mem. That's counterintuitive to me. Let these memory locations do that. So we place them into all the registers. No, I don't know how those values got into the registers. In fact, where are all the in commands? There are no in commands in here. Yeah, I think I'm missing something. Anyway, I do want to look at these. So we'll take a look at those. Callaghan, hello. Um, okay, so you're saying about the dynamic live assembly. Are you printing instructions as they're executed, or are you printing them in the order as they appear in the binary? Okay, so this that I was printing earlier in the REPL, this is dynamic, this is live. So this is as it's running. And now this that I'm doing in the REPL, or not in the REPL, in the worksheet, this is directly from memory. So I've done both. And well, the problem with this is it's 11,000 instructions because loops, recursion, some sort of thing. And this one here um, should be easier to understand, right? So this probably appears in that output, but it appears many times over. But it appears in the memory only once because it has that specific memory location. So let's copy worksheet output, have a look at that. And yeah, select to count cars. I'm not sure what you meant by that. I think I missed it in the moment. How are you getting those lines, those print lines to pop up? Oh, yes. So this is the magic of a worksheet in Metals. So Metals is a language server protocol implementation for Scala, and you could get this in VS Code or Emacs or Vim if you're one of those people. Yeah, and it gives you live commentary on the code. So this runs it. This is like a big multi-line REPL basically. So it's a multi-line REPL where all the output is shown as a comment. So this is everything that goes to the standard out goes to these instead. So it's really nice to work with. I use it for Avena code, and some of you might have seen like me having stream problems where like I run an infinite loop in my worksheet and it crashes my computer or something. Well, it turns out the worksheet wasn't only like the worksheet was a problem, I think. But the bigger problem was that my stream encoder, I was doing software encoding instead of hardware acceleration. So I caught that issue. I don't know what that happened. I think I did an OBS update and reset the settings. So you haven't seen my stream stutter, um, because it was all competing with my video encoding. And I did a couple other optimizations. So now my WSL instance is only limited to 12 cores, and my JVMs are each only allowed 10 threads. Um, so I can't bring myself to a grind anymore, which I should. Like, it feels like the professional thing to do. So I guess I'm slowly becoming a professional. Anyway, I'm stalling again. We should see this output. Oh boy, look at that. Oh, no, no, no. This is not all the output I wanted. I wanted this whole worksheet. Copy worksheet output. Yeah, it is a really cool little tool. Okay, so here are my functions. 3 functions of interest. Now, I do find it very curious that they all push, like, when I've implemented a language on a stack-based VM before, I don't know if I remember. So you call a function, right? You pop all the parameters to that function or the arguments to that function onto the stack, and then you jump to the address, right? Um, do you? Then you jump to that address, and then you would actually, let me not think about that because that's just going to distract me from what's actually going on here. So here, I find it curious that after the function is called, there's all of this pushing of different registers. So each function pushes into different registers. Or no, you push from different registers into the stack. So depending on what happens before this function is called, different values are being pushed onto the stack. But also, what's interesting is that the values are from different registers, right? So this function uses the parameters in these registers. This function uses the parameters in these registers. And it's weird that it's not just 1, 2, 3 each time. Sergeant Pepper, welcome. You've heard nice things about Scala. Well, you haven't seen me coding in it yet. So I don't know, I might change your opinion. It was always a little bit of excitement. It was too much excitement for me. Um, yeah, because one or the other might crash. I think one time my stream actually crashed. Hmm. Okay. So we push R2 and R3, then we do stuff with these. So R2 and R3 are free, right? And then we set into R3, so R3 equals R1 plus R2. And those are dereferenced. I'm just going to do that. I'm abusing C-style syntax here. And then R3 equals not R3. Oh, thank you, Copilot. And then R1 equals R1 or R2. And then R1 equals R2 and R3. So all that happens is that the register 1 is set to an expression, and then we pop these back. So we pop R2 and R3 back. So we popped the values that we were going to use to store temporary values, right? Well, actually, R2 though. R2 showed up in here. The thing is, R2 never needs to be push and pop. If you were to delete this push line, push the value of R2, and then pop it back here, R2 is never overwritten. So the push R2, not necessary, right? So the entire effect of this, how do we do this? Let's just do some substitution. So R1 is set to the value of R1 and R3, where at this point R1 is R1 or R2. So R1 or R2. And R3 is actually not R3. So not R3, where R3 is actually R1 plus R2. R1 plus R2. Yeah, so R1 is set to the value of that. Okay. And can we think of what this is actually doing? So you mask it by R2, and then you AND it with the inverse of those two added together. That's what this function does. It sets the value of R2. So we could look at places where this is called. Let's see, I want to get the actual address of that. So if we open up our play, I mean, I do have the actual address of it, but I want the hex address now that I have that. So that's 084D. Oh, wait. 084D. Right. Register still one based. Yes, the registers are still one based. Their names are one based. The underlying array holding them is 0 indexed. Where's the add from? Oh, add? You are right. That was an and. Good catch. Thank you for that. So R3, this first one, R3 equals and R1 and R2. Okay, that makes more sense. Okay. So the not of the and of those two, isn't that just, let me think. So bitwise, if you not it, well, let's just do the and bit first, right? So with and, only if they are both ones is the result of that bit 1. And then we not it. So that means if either of them are zeros, if either of them are, so this is equivalent. Correct me if I'm wrong, but this is equivalent to using De Morgan's law, right? That's equivalent to that, right? These are unsigned 16-bit. And when you AND these two, I wonder if there's some algebra I can do on this. So you're ANDing the OR of them, and the not OR of them, or the OR of their nots. Is this XOR? R1 or R2, and not, oh, yeah, and not R1 and R2. This is XOR, exactly. Oh, you're right, you're right. So that's XOR. Cool. Good catch. Good catch. Okay. So we know that that's XOR, and we can implement that one faster in memory. Um, I want to look at, so this is the log somewhere here. What's this? Oplog. That right. So this was after the teleporter. Oh, here we did a map one. I think we want the instruction themselves too, though. This is what's happening when we are running the use teleporter command. Um, it's interesting that I'm not seeing any ins, so I think I might have to debug something. But let's see what the first call is actually. Call 0623. So this I want to call. Or I want to inspect. So let's go to our play worksheet. 0623, cool. We can leave a comment here. This is XOR. So it's the XOR specifically of R1 and R2. So save into R1. R1 equals XOR R1, R2, right? Yeah, that's what that does. And going back to our scratch, right, we found that other function of interest, but going up here, I don't think I want to print just the instruction. We want to print the contextual information around that too. So the map one, this one here. Nope, nope, nope. Where is it? Here's a print line of everything after the feed. So after that, I'm going to do emu equals emu.clearlog. And then we progress output. We'll print line that. We use output. Okay. Um, and then this size should become smaller now because we cleared the log first. And this bit here, we just want to print the whole thing. So we'll remove that map. Okay. Copy worksheet output. Scratch. All right. So here was that first function that gets called. Push R2, push R3. Set R3 to R2. Okay. Set R2 to that value and call a different function. Interesting. You know what? I just had a thought. We'll go back to the worksheet real quick. And in this op log, I want to look for anything that has an R8. So how do I do that? I guess let's start with this. Emu.oplog, and we'll get the strings that map. So these are the string names. Dot filter contains R8. Oh, and let's do it for each print line. This should be interesting. Jump false. If it's 0, you jump to 1-5 e5. Okay. So I want to set the value to something else first, and then see what happens. Yeah. Okay, so set the value to something else before using the teleporter. So emu equals emu.setRegister, registers reg.r8 to, I don't know, 42. So u15.from int. Okay, quick sidetrack because I'm getting tired of typing that warrant. Numbers package. We need an extension on int. Oh, there is a toLit. But I think I just want all of these. toLit. So 2u15. Right, let's turn on Copilot here. To address to reg. You want register from int there? Yeah, I think so. Def to reg ID. So we still want the reg, but we want reg.from index. Or, as reg index. Right, we would do that with an index and this one to register as reg index. Okay, that'll be nice to have. Okay, so we set the register and then we use a teleporter and then we see what happens. Well, hold up, we want to do this before feeding, yes. And then now we could look for mentions of R8, and now there should be multiple, not just the one. No, it's still the same one. Jump of false, R8. R8 is 0, so it does jump to 1-5e5. But otherwise it should go to 155, 154C. No, not C, D. No, actually E, just the next instruction. We could bypass that. I think we're supposed to bypass it, actually. So we progressed the instruction pointer. So our loop after feed, I think so. Wait, I don't know, actually, where the XOR is used yet. But why didn't changing R8 do anything? Let's just do a count. We set register and then we use the teleporter. Right. So the count of this. Oh, I know why it's not rerunning it, because we're not compiling. No, that's not an issue. That is a spurious warning. Let me just make sure we can compile here. Okay, yeah, it's compiling just fine. Starting emulation, yada yada. Uplog show. Okay, and now this time it's showing the address as well as the instruction itself. So the one that's interpreted contextually with like the values inside the registers. But why is my worksheet not updating? So we've got the count here. Is there something else not compiling? No. Try without modifying the reg. Well, here's the thing. This should have output right here, right? So this hasn't even run yet. So it hasn't even run while trying the register. So here, it's still the that's still what it was before. Let me see. I think it's possible that my metals worksheets have died altogether. Exiting BSP. Okay. Something may be wrong with the current configuration. Run clean. Subcommand to clear the working directory. Okay, yeah, my worksheet just died. Failed to run request with params. Yeesh. Okay, so metals, restart build server. And while that's happening, yeah, we'll give that a second. And whoops. While that's happening, let's go back to our scratch and let's look at those other functions of interest. So here's the XOR. We'll eventually want to look at all the times that's actually called, but it's probably not the most interesting. Like maybe there's a multiply function actually. So R1, R3, R4, so many variables here. And ultimately, oh, there's a jump if true. Jump to R2. R2 is going to be R2 plus 1. Okay, let's start from the top. So R7 equals R1. R1, I suppose, is something that needs to be passed in. R6 to R2. And then read mem R5 into R1. Is that how read mem works? Let me just check my docs. Inst. Case rmem. Read memory address B and write it to A. I think my hacky 2 string. I was going to say, I want more type information, so it just tells me what these are, but we can just learn what rmem is. Read memory at address B and write it to A. So B is an address. So the address from R7 okay. R5 equals mem from R1. And that was after setting, so R1 equals R7. Yeah, let's make this a little bit more like English. So R6, I think that's R6. Wait, am I doing it backwards? Set register A to the value of B. Okay, so this is actually R7. R7 equals R1. R6 equals R2. So we can infer that R7 is probably an address, right? Because we were reading the memory stored in R1. So if we see that used again, then we set R2 to 0. And we add 0 to R4. Or I mean, we add 0 to 1. So this just sets R4 to 1. So R4 equals 1. Right. Let's just write it out explicitly. So R2 equals 0. 1 plus R2. Okay, weird. And we check. So greater than, how does that work? R1 equals, if B is greater than C. So if R4 is greater than R5, then 1 else 0. Where R4 and R5, we don't know anything about yet, except that R5 is from the memory stored at R1. Did I notice any differences between the teleporter? I haven't noticed yet. I was reloading the worksheet because it died. So let's see. Has it been able to run? Fuck. I'm just gonna restart VS Code because I would like to see too. Right? I want this line to give us a difference. But also, I don't think I ever actually saw a difference when I ran it here. Right? I went all the way to the teleporter and I switched the value of the teleporter of register 8 and then used the teleporter. And both times I got the same number of instructions. So that was weird. So maybe there's something that's forcing it to be 0 and I have to bypass that. Because the book did talk about bypassing, right? Let's see what it says. And I'm going to restart VS Code in a sec. Or you know what? I had this in a gist. Let's restart VS Code. Give it a sec. You know what? Let's just kill all Java. That's a good thing to do every few minutes, right? Um, start that back up, and then we'll run SBT. And we have that gist. You know what? Just do. Where is my strange book here? Yeah, I definitely want to try again. I want to try again as soon as I can. Because I expect it to be different, and I don't know what I missed earlier, but I think maybe that was just my brain missing something and not actually the computer, right? The confirmation mechanism would be very computationally expensive. While this would likely not be an issue for large-scale teleporters, a handheld teleporter would take billions of years to compute the result and confirm that the 8th register is correct. So it's not even doing that because it would take billions of years, unless it's just really fast for 0, but like it's short-circuiting. We see the jump command, right? So if you find yourself trapped in an alternate dimension with nothing but that, you'll need to extract the confirmation algorithm and re-implement on more powerful hardware. Yes, that's what we're trying to do, extract the confirmation algorithm, which means the address past the jump false command, right? That checks if R8 is 0. It should at the very least allow you to determine the value of the 8th register, which would have been accepted by the teleporter's confirmation mechanism. But also, here's the thing. Changing the value of the 8th register, this is what you're hinting at, Zuno, right? If we change the value of the 8th register, it should start running that confirmation code. And then that should allow us to determine the value of the 8th register, which would have been accepted. And then we need to put that value in. But the way we bypass that is by just skipping the jump command. We also do want to bypass the confirmation mechanism because it would take too long. So I assume then that it'd also take too long for a wrong value. So maybe that's what I haven't seen. But let's pull this back up. Oh boy, I feel lag. Failed to evaluate worksheet. Timeout reached. Oh yes, okay. Timeout is being reached because of this 8th register. We need to limit the number of this progress until blocked is too much. So let's comment that out. After we set the 8th register, we need an alternative to progress until blocked. So like 1,000 at a time. Like progress some number of times until blocked. It needs a parameter. Def progress until blocked. I want to make this loop lazy, and I only get what I need. Okay, I'm gonna use the bathroom, and then I'll come back here and do that. Did I ever change R8 in the game? Yes, I did. You know, let's try that real quick, and then I'll use the bathroom. So here, let's jump to our shortcut. And then we will change the teleporter value. Actually, yeah, we'll change the teleporter value. Okay, so get R8. Oh, nope. Whoa, what happened there? Number format exception. Okay. So I use toInt option and not toInt. So get R8. Invalid register index. Or are we 0 index or something? Yes, yes, I think we are. That's not good. Okay, so in both these cases, we take I. Register from index. Okay, here's the thing. The from index, let's go package. I have two different methods here. So from int gives us like the word, right? Which is not 0 through 7, but has a leading bit in the 16th place. So there's a leading 1 bit. From index, the idea here was to be from 1 until 8. So I guess we need to take I minus 1. Okay, to get an actual register. And then the names will be, I did this to myself. I did that to myself. And you know what? I still don't regret it. Okay, let's change R8 in game. So we are at the ruins. Let's make this bigger. Let's get R8. It should be 0. Wait, look. Get R8. Okay, yeah, the value is 0. Let's use teleporter. Okay. Oh, we forgot to enable the oplog. Okay, so oplog toggle true. Oh, it's gonna try and run the whole thing anyway, isn't it? Because it's no longer printing in line. In my first implementation, I did printing in line, like as it's streaming, but it's gonna try and complete everything first. It's not, and then give us the output afterwards. So I need like a live oplog. Or not even an oplog, just like live tracing. I need a trace parameter for that. Okay, so let's try it anyway. So set R8 142. It could be the case that I never actually set the value register 8 because as indexed wrong. But now let's go, what is it? Use a teleporter. And that's just never gonna end. It's never gonna finish running. Not unless we do emulator. Okay, so let's do if oplog enabled. I've got the solution here. So if oplog enabled, then we'll print. So we'll just have that work differently now. Oh, Copilot's messing with me. Then print line inst dot or wait state dot show inst as we're looping. Yeah, so we have that happen as a side effect. And then the whole enqueuing state, whatever, that can still happen. Yay? Yay, question mark? No, it's progress. Great, so let's look oplog toggle. So that's enabled. And then now we set R8 to 142 and then use teleporter. Okay. This is what's running, and this is what will never finish running. So I'm gonna use a bathroom. Maybe it'll finish. Is it done yet? Okay, we're not crashing yet, but see, it seems smooth. I have outsmarted the JVM here because, oh wow, we are still lagging a little bit. We only have 12 cores, and they're not even all running full bore. So Windows gets 4 cores. We get 4 cores to run the stream. Yes, repeating pattern. There's probably some sort of loop. What I think what I want to do, I want to do something similar to what I was doing earlier, and it's looking for the thing that gets called most often. Maybe, so call commands, jump commands. If there's a loop, it's going to be with a jump. So I'm going to look for a jump command that's repeated often. So I think maybe I'll run, I don't know, like 20,000 instructions. And I'll look through that log for calls or jumps that are repeated over and over again. The one true Bob. He switched to Twitch. Well, welcome. Oh wait, are you Bob Null? You're Bob Null from YouTube. So my YouTube delay is longer. I have it buffered in case, so it's like my VOD source. So I have it buffered in case I'm lagging or something, so that the quality stays high. So it's gonna be like slightly higher quality, slightly higher bit rate, and has no music. That's the difference. But welcome to Twitch. The ad seems somewhat unique. Maybe. If we stop this run here right now, we do see a lot of return calls. Call, return. Are we seeing jumps? Jampy. We're not seeing jumps. So it is not a loop. It's a function that does no tail recursion. So 999 plus calls. 178b. 178b. 0x 178b. Okay, there's our function. Let's go extract that. So I've been hoping to do this in the worksheet, the part where I look for this function. But it seems that's unnecessary. Cool, I'm glad you like the music. I chose it to fit with the Synacor theme, so I've been going through like playlists of like 80s, 90s synthwave, CRT synthwave. Okay, so we no longer need to do the step in the worksheet where we crash the worksheet because we have our address right here. So I still kind of want to make this here lazy, but we'll leave that as a to-do. To-do, make lazy. And what I could have this do is this loop could return a lazy list. And we just construct that lazy list recursively. Right now it is tail recursive, so I was thinking I wouldn't have to worry about performance, but if it's big, it's big. I really just want the lazy list of ops. I suppose you can unzip a tuple, a lazy list of a tuple into something else. Okay, that's a to-do for later. Let's go back to our worksheet. Again, the address was what? 178B. Okay. Let's make sure this stays commented out so we don't crash the stream. And let's look at this. 0x178b, 178b. Oh, no. There we go. And I do also want to see the code. I want to see the code that runs after the jump faults. Right, so the code that's after this R8. So we can just extract from there. It'll find us the next return. And then the first call we see in there, we can extract from there too. I suppose we don't need to do, okay, for each print line, that's fine. Progress until block size for each print line, sure. I still think it's suspicious we're not seeing the in calls. I think my op logging is skipping ins. And I feel like that was intentional at the time. Is the worksheet still dead? Yeah, it's evaluating the worksheet. Sure. I don't want to have to run this in an actual source file. Compile request is taking longer than expected. Over 10 minutes. Yes, compilation should never take that long. Yeah. Yes, rerun it. Why? Oh, we've got issues elsewhere. Right. I don't care about those right now. In fact, I thought I had fixed those warnings before the stream. Okay, bloop. Press to reconnect. Okay, I guess I just have to restart the server. Activate the teleporter, bypass the confirmation mechanism that takes too long. We know exactly where to look. We know exactly where to look. We could be done tonight if it's really easy to understand. Then we just have to set that and bypass the confirmation. Well, okay. You have to understand the confirmation code in order to know how to bypass it properly. So we want to extract the code starting from that first JF. And if we can do that, okay, here. Are we running? I'm not seeing anything running. Yeah, these are always kind of frustrating moments when the worksheet kind of poops out like this. Especially when I feel like we're so close to finding what this is. Hmm. Like we could try reading the raw file. Actually, no, that's gonna be a pain to debug. But we definitely do want to extract this function. We could just extract these 5 functions and the JF. I want to know where that JF is. Oh, you know what? Wait, we had that in Scratch, don't we? Um, let's search for JF. Not that JF. You know, these I think are address locations within this. I think when I extract the function, I should also give the address of all of these so we know where we're jumping to. Okay, good to know. Wait, there's no, okay, there should be an R8. JFR8. Here it is. Oh, and we do have the stuff that's afterwards. So at this address, this is what ran. Oh, I should do a swap on that before running it so that the addresses align. I'm just going to do that real quick before I forget. .map. Um, so we do for each print line somewhere here. Okay, so .map. So we swap the order of those. And then we for each print line. Okay, but we jump to this address here. Jump if false to 0x15e5. Oh, that's right here. That's the next line. Wait, what? We jump to the next line if false? Okay, case JMP. Or jump false rather, JF. If A is 0, jump to B. If A is 0, we jump to B, 15E5. B is the next line. So if A was not 0, we still jump to the next line. Right? That just becomes the next instruction. How is it implemented? The VM state case JMP. Yes, I am inside the matrix. Exactly. I see it all. Our world is a sham. Def tick. Okay, at some place here we are. Oh, why did it add the Synacor dot and all of that? I don't like that. Okay, that was not necessary, but JF is here somewhere. Okay, if A is 0, then we jump to B dot value. Otherwise, we progress. And progress is just skip ahead by the number of parameters. And skip ahead by the number of parameters. Wait, 154. No, okay. B. So there are how many parameters? JF, 2 parameters. So C, D, E. So 154B. So this did jump. Jump if false. If that is 0, jump to that. Okay, right, it did jump to there, exactly. Right. So the code you want to see is at 154B plus 3. Or B plus, okay, B is the address of this, C, D, E. Yeah, plus 3. I can leave that there as a note. So let's go open play. All right, another point of interest here. 0x154b plus 3. And we will print from there. Um, why was this interesting? Do you remember why 178b was interesting? Um, I can't remember. Like these four were just called often. Let's look at our scratch 178b, 178b. Nope. Oh, right. Yes, that's from our REPL. Yeah. Okay, the forever loop. Exactly. Yeah, that's the most interesting one. So this leads up to there. And then these other three were just found in the wild frequently. I think 623, these were the three most common instructions we found at first. I can't remember exactly what this was, but whatever. These two are obviously more interesting. So this bit, it looks like I can't run the worksheet. So I'm gonna put this into like another main method. Um, let's just make a play.scala file. And those bits I want. So, I guess there's all that. I don't mind if that all prints actually. So we can just take everything. Memory, resource, yada yada. This is the first function we ever extracted. At main, def. Let's put this in a package. Package, Synacor. Main def play. Yeah. And we just indent everything. And we do each of these print lines. Let's add the memory address of print line 0x84d function. Okay, Copilot, you can do this. Alrighty. And let's make sure that danger line is commented out. Cool. And let's run SPT. Nope. Run main Synacor.main. We want Synacor.play. Hey. Oh, I would wanted addresses in there too. Ooh, this is a long function. Okay. So that we get to decode. I was hoping it'd be simple. And then this is the 0683. No. That wasn't a function. This last one, let me just double check. This last one, 178b. This is from the infinite loop, or 154b is from the infinite loop. Just check again. This 178b is from the infinite loop. From infinite loop. And 154b, this is the plus 3. Plus 3. Um, runs after failing JF. Okay, so that's a breakaway bit. Let's open up Scratch 2. Because now I want to look at this output here. That function, that function, that function, that function. And here's our XOR. Oh, what is all this from? Oh no, that's just my list of all my calls. Right, functions and how often they are called. When you when you have R8 set to 0. Okay. Oh, I'm struggling even with this select. What? Is it possible to also print the address of each instruction as they execute during your output? It absolutely is. Yes, I did want to do that. That'd be very helpful. Let's go play.scala here. Okay. So for each print line, extract function, let's go to extract function. And we're actually printing too much other stuff. So I'm going to take some of our for each print lines and comment them out. The call counts, yeah, we can comment that out too. Print line, op log for each print line. Yeah, it's one more right here. Okay. Now, when you go to extract function, you want a list of instruction and also addresses. Address and instruction. And I think that should suffice, yeah. So inst, get address to inst, and then loop along. And in this case, nil. Yep. Okay, let's try that again. Oh, we have an issue. Loop address. That next instruction, that should work fine. Oh, this here also needs to have address and instruction. Cool. Function from infinite loop is actually, wait, tiny? It just has those two calls and then it returns? It hits a return already? No, but there's a jump true. The jump is skipping past a return, isn't it? Okay, that's a little bit annoying. We need a modification that counts returns. Okay, let's do that. I'm just gonna assume there's one return for now. I suppose I could make a stack. Except, the jump true doesn't necessarily need to be well formed, right? It doesn't need to be skipping over a return. So we can't always assume that jump true has an associated return. But in this one case, we can make a special case. So extract function, and we allow one return. Return equals 1. I'll say ret equals 1. So it's passing this parameter, extract function, ret int. Let's default that to 0. Okay, now instead, so we'll have this int to match. We have ret being passed along here. Int, well, I guess we'll also default that. So when we loop, we don't do ret minus 1. We only subtract it when we get here. So if ret equals 0, then we do nil. Otherwise, we loop so address onto inst.ret onto a loop where we subtract ret minus 1. There we go. So now in this case, we should be able to get past whatever's that jump that skipped. No? From the infinite loop. If ret equals 0. Oh, right. We never actually set anything else. Loop, we need to pass ret along here. Ret. This inner one shouldn't be defaulting. That causes bugs. And here we just pass along ret. Pass along ret or ret minus 1. I'm wary about default parameters. If they can be forgotten, I don't know. Okay. Hey, this looks much better. It ends at a call that follows with a return. Okay, so there's a jump true, ret, and then there's another jump true, call, and then a return. I think we need at least one more. Okay, let's increment that. So ret equals 2. And let's just keep running that. All right. Sorry, this is tiny. Let me make that bigger. Okay, so we have to jump true, return, jump true, return. And the jump true jumps to something that's past that. Oh, we need to be reading that in hex. Okay, we need our own print function, def show. And yeah, we'll show the pair. Wow, Copilot got it. Copilot got what I wanted. I don't want to do inst.show though, because that's not necessarily going to be true, right? The register values aren't going to be correct. So we want just inst.toString. Okay. Now let's see what it did. And also, did I update that from? Oh boy, this is really long, whatever's going on here. Okay, so here's the infinite loop. Jump true, followed by return. And the jump would be to 1793 if that is true. Otherwise, we'll eventually hit up this return. Another jump true. Something that's very well. Oh, wait. No, it's not showing that properly. Address.hex. Oh yeah, we never updated. So let's replace it for each print line. For each print line, we're replacing with for each show. Yes, let's do that. But we need to have a print line in here. So this is going to be unit, and we're just going to do print line that. Okay. Amir, hey, hello. Okay, that's a little bit more useful. So we jump if true to 1793, yada yada. And here we have a jump if true to 17AO. So we can use that address to give us an address that we jump until, right? So we have to get at least that address before we can return. So we don't have to manually say how many returns to keep. So we only return if we've hit past a max jump. Now that's assuming that we never jump out of the function itself, which I suppose would be totally legal. So this jump if true goes to 170A, and then we have a second return. We don't want to end there yet, though, right? 170A, 7FFF. This is well beyond us, actually. So we have an address limit. I suppose in the case of a jump false, we can, or jump true, either one. In case of any jump instruction, well, no, in case of jump true or jump false, we can increase the max address. Yeah, I think it's much longer. I agree. I'm just trying to figure out how long I should keep going, because you can't just go until any return, right? The final return will be after the biggest jump that we ever see. So we can just keep track of the biggest jumps that we see. We need to extract a function that has jumps. We'll just say with jumps here. So target address. I don't know. We have the biggest jump, I guess. Last jump. So we want to keep going past the last jump. And we can default that to address, I suppose. Can we do it that way? Yes. So if address is greater than last jump, then we can return nil. Then we can stop going. That is our final return, right? Otherwise, in the return case, we don't need to have this line anymore, but we do have a case handling jumps. So case ints.jf. I think all those called into the address is all within the last block. I think they would, except some of them are big. So this one here, it calls still into here. This one here, 17A0 calls to here, but we have we might have more. Oh, wait, all the jumps we've seen? Jump true, 1793. You're right, it goes right here. Jump true, 17A0 goes right here. You don't see any other jumps. You see a couple calls, 178B, and we have another 178B. And I think we have parsed 178B. Oh, no, that goes recursively. This is a recursive function. Cool. Lovely. Yeah, that is a full function, isn't it? Good catch. Thank you. Thank you, Bob. You saved me from making something I didn't need to make. Okay, so let's copy that. Let's copy the others. So that's a function from the infinite loop. Here is some big one that was called a lot. Why am I not able to? So I'm gonna make this really tiny for a sec. Because for some reason, I can't like scroll up nicely. I have to go line by line here. You find it a bit amusing that the challenge is being nice by not throwing unaligned instructions and self-modifying code. Oh my god, that would be such a nightmare. I mean, it's totally possible, right? Yeah, yeah, that'd be a real nightmare. We'd have to write like a proper decompiler, and we'd have to like keep track of the actual function call graph and all that. Okay, technically, good. Interesting to know. Um, yeah, self-modifying. There'd be some true ROM hacking. The ROM hacks itself too. Okay, so scratch two. Function from the infinite loop. Should we look at that first? I'm kind of curious about this one. Wait. Here's what runs after failing JF. And this is actually pretty big. So where are the calls from here? Because seeing what it calls, OX5B2. OX5B2, that's a recursive one, right? No. Don't we have OX5B2 in here somewhere? No? Okay, so it calls that. There are a bunch of no-ops for some reason. It calls 178B here. Nice. Oh, look at this. Is this a result of 178B? This is the expected value right here. 6. Wait, 6. Hold on. Equal to R2. Um, wait, check if R1 and that are equal. Does 178B set its value? And R1, push R1, set pop add. Was it that easy? It can't be that easy. I don't want to be done tonight. R1, jump true R1, yada yada. That is a value, right? That's not a register. Actually, I don't know. No, if it were a register, it'd say R. So jump true that to 179. But at what point does it do one R8? So you set R2 to the value of R8 and you do stuff to check, I guess. Where else is R8 used? Well, here's a call to 178B. And then this stuff here. I think, well, this is the code from the failure case, isn't it? Or from the, this is the code from the case where we do skip this. One, yeah, from failing. So, right, this stuff doesn't actually even matter. Wait, it is interesting to me that it does still call 178b. Right is never referenced here again, right? He thinks it's easy. Of course not. Of course it's not easy. If you look at pre-post memory, yeah, I still want, oh yeah. The self-test technically self-modifies. That's interesting. I'd like to see what changes. There's still a bunch more codes to verify and to readme. Really? I have 6 of them, right? So I assume you get 7 and 8 by 1 completing the game and 1 jumping um, to the wrong location. So 1 by bypassing the self-check or the R8 check, and 2 by bypassing the R8 check and also getting to the right place. Okay, so let me restate this. So this stuff, we jump, this doesn't run after failing. So, or this would run if we didn't jump, right? So this is what would happen if R8 was set to something else. So runs after R8 not equal to 0. Let's make that very explicit here. Okay, and R8, set the value of R1 to R8. And is there an equality check? Well, here, set R2 to R8. One seven eight B, 178B. There's this call to 178B, big ol' function, and then we check what R1 is. And R1 is R1 plus this max value. Yeah, that is the max value U15, right? And we're checking if that's 6. So after this call, I think we want that to be equal to 6. So this is R1 is equal to R1 plus 7FFF. And it would overflow, right? So we're not checking if that is equal to 6. Okay. We can look at that value, but what else is happening before that? R1. Wait, we pop R1? We pop the value of R1 before doing that. We pop the value of R1 and then we add R1 to it. Or we add 7FF to it. We set R2 to the value of R1, and then we pop into R1 something off of the stack. So we push R1 before calling. I should just decompile this properly. So let's read this. Um, I'll write below. I'll read it on the right. and I'll write it here on the left. So let's say if R1 is equal to, no. We jump to R1, or we jump to 1793. So if R1, then go to 0x1793. And we'll see what that is later. Otherwise, we add R1. R1 equals R2 plus 1. And then we return. So we just increment. So let's just say, no, we increment 2. R2 plus 1. Return with R2, the R1 set to that. Okay. Do that and then return. And then if R2 is equal to, oh wait, if R2, then go to that. And here we add R1. R1 equals R1 minus 1. I don't think we'll be able to just pull out the value, right? We have to run this on hardware, figure out what's competing, and run the confirmation. It might be a reversible function. If we figure out what's competing, we either reverse the function or we just brute force the function until we find something that gets us what we want. So like based on R8, something happens to R1 is what I'm guessing. And if R1 ends up being some value, then we're good. Okay, so jump true, otherwise add to R1 7FFF. So this is minus 1. Is that really true? So the max value, if you add 1 to that, that becomes 0. Right. So 1 becomes 0 when you add the max value. Okay, that is minus 1. Cool. R2 equals R8. R2 equals R8. And then we call, what's with this R1 equals? So we call, and since the function depends on what R1 is, we're essentially calling with R1 and R2. The first things it does is play with R1 and R2. So call, we're essentially kind of passing R1 and R2. Okay, so we call recursively and then we return. So if R1, then we go to, here is that code, 1793. We don't go to 1793. No, the first one, we go to 1793, right. And then this is the other jump. I see. So R1 equals R2 plus 1. Is this a like Ackermann function? This is sounding like the Ackermann function. But let's see. And after this return, we have this. Yes, there's a final return after that last call. I just didn't add it in. Whatever this is, it is really slow for sure. So we push R1. Why are we pushing R1? So we push R1 onto the stack. Did we ever pop? Okay, so we give ourselves a free variable. So push R1, and I'm going to indent everything else to show that we're not there yet. Actually, here, Copilot. Do I let Copilot translate this? I'm still going to verify by hand. So R2 equals R2 minus 1. Okay, and then call of 178B. Already so fast. And then after calling, wait, we still pass along the same R1 function, right? And then R2 equals R1. Set R2 to R1, pop R1. So I'm going to indent this stuff because now we have the value of R1 back. R2 equals R1. R2 equals R2 minus 1. And then R2 equals R1. But this call changes the values of R1. Changes R1, maybe? Let me catch up here for a sec. I can't go to your LinkedIn profile, though the link you put on through the link on my YouTube profile, you can't go. I'm just too squared on LinkedIn too, so probably I mistyped the link somehow. This guy is good? You mean me? Thank you. String comp. But it's fucked up because it has two functions for each index. Oh, you think this is string comp? And R1 equals R1 minus 1, and then we call again. Really? Wow, you saw that fast. Let me see. Okay, if R1 is anything but 0, oh, this is trying to go down to 0. Otherwise, do this. So R2, well, R1 equals R2 plus 1. If R1, then we go there. So we have some values for R2 and R1. I think we'll need to look at the call site for 178B and see what kind of values are put in. So we decrement R1. So if R1 is positive, then we decrement it. And we set R2 to the value of R8. So we can assume it's positive the first time. We decrement it, set R2 to R8, and then we call again. If it so happens that R1 has reached 0, then R1 would get set to R8 plus 1. And then we would repeatedly decrement R1. So this would return, right? Yeah, that's done. Once that hits 0, we jump here where we decrement it. And then we call this function. We decrement R1. This function, am I reading that right? Yeah. So if R1 is positive, we decrement it and recurse, which adds R8 plus 1 to R1, and then returns. So then, yeah, we decrement it and then add R8 plus 1. right? If we immediately call this, then that -1 didn't really matter, did it? Right, because we call this, we go back here, R1 might still be positive, and then we add a shit ton of numbers to it. And we go back here where we're decrementing. We decrement, we add a shit ton of numbers. From the end, you can see it as a while loop. The calls are continue. Oh, yes, the calls are continue. It has been ages since I've used a continue in a while loop. I don't even use return. Like I don't like doing a break in a function. Specifically, well, I mean in Scala you never need that. Like you can do it, you never need that. But also because of this, because it's hard to decipher. It's hard not to decipher it in proper code, let alone bytecode. Okay, so here we push R1 out of the way. R2 becomes we decrement R2. We decrement R2, and then we go back to the top. This is continue. We decrement R2, we go back to the top. Once that top call finishes, then we actually come back here, and R2 equals R1. In this case here, we go back to the top, we call that, and then we return afterwards. Yeah, I need to run through this with examples. But we can totally implement this, right? R2 equals R1. We pop R1, then we decrement R1, and we call this. Having set R2 to R2 minus 1. Yeah, let's let's do that. We're gonna call that. Except we don't need to do the push and pop because we're not reusing registers, right? We can just pass along those values as a function. And continues our jumps. Yeah. I mean, not all the time though. So in Scala, if your function is tail recursive, it will be compiled down to jumps. It will be as efficient as a while loop. Yeah, push and pop just restore R1 after the call, exactly. But we don't need to be like restoring it because we in code we actually just have values. We can ignore push and pop and just have that be like, I don't know, a recursive function or something. Wait, before we go there, so we get the general idea of this, right? This is this mutually recursive whatever. It has to do a lot of decrements. We have to make this efficient because this takes forever. It's something that looks like the Ackermann function. Let me just look up the Ackermann function because if it is that, then at least seeing it would help us recognize quicker, right? Ackermann function. Oh, wait, yeah, that involves multiplication. Okay, but it's something like this that is doing this loop of a bunch of plus ones and minus ones. Or wait, no. Where's the actual definition? Definition. Okay, it is the Ackermann function. So a of 0 n equals n plus 1, a m plus 1 and 0 equals am and then 1, am plus 1, n plus 1. Yeah, isn't that it? That's exactly it. No comment. No comment, says Juno, who absolutely knows it's the Ackermann function, has been letting me sit and squirm with this forever. Okay, yeah, I'm just gonna turn on the horse blinders now. If I squint, that looks close enough to the same as makes no difference. Yeah, I'm gonna squint. By squint, I mean just like close my eyes and pretend it's good. I don't need to do that. I just need to know what's going into it. Um, great. So how do we skip over the Ackermann function? Um, what are some like table values here? Okay, here. No. What's S? Successor function? Um, when is this done and where is its value saved? I guess its values are saved to register 1 and register 2, right? This is setting the values of register 1 and register 2. R1 before call, where would the final return be? As soon as R1 is positive, I guess, then we return for good. But the first call has to do like all of this and then return for good. And this branch here, decrement R1, decrement R2, do recursive call. When exactly is the final end condition? There's a return here, but that return is always after this call. So we call recursively, and once that returns, we can return from here. This one here ends with the, oh, I mean, there's an applied return down here, right? So we can end from any of these. The fastest way out. Okay, this ends with a call. This ends with a call. So anytime we go here, we do recurse one more time, actually 2 levels deep. Anytime we go here, we always recurse one more time before returning. So I think as soon as, let's say this is the very first thing we enter, right? Let's say R1 was 0 when we entered. I should just look at the Wikipedia page for Ackermann function. Okay. But I think more importantly, we need to see what's being passed to that. So we need to look for calls to 01768B. How did I know what it was? I don't know. I don't know when I first learned about the Ackermann function, but I have a math background, so it might have come from that. I might have heard it in a CS class. It's just, yeah, it just comes with Scala. You just learn Scala and you know stuff like that. Yeah, either a comp sci class or some math book. Now this stuff is a thing that okay, so we call it that, and we check if R2 is equal to R1 plus 6. And I think we had made an assumption here about what the value of R1 would be. So we call 178b, then we check, no, we store into R2 the value of R1. So all we care about in here is what R1 gets set to. So we need R1 to be equal 6, right? And how do we get that to return 6? I don't know, but we'll figure that out. So R1 needs to be 6. So we can just inject a function, like we can skip this whole bit by injecting at this call site. Oh my god, we can totally do this right now in the REPL. We can do this. Wait, set R1 to 4. Oh, hey, here are parameters. R1 is 4, R2 is 1. So we can run that through. Um, but we need to inject here. Let's just inject a jump function here. Whenever we see call 0x178b, we can just, I'm totally going to do that. You could never crash out or reverse engineering ASM with me. It is ASM ASMR. It's REASM ASMR. We've got this. We've got a hack. So let's go to vmstate.scala. And I just want to see what happens. Right, let's keep this thing up here open on the right so that we can see what hacky values we want. And then we jump false on R2, which means R2 must be 0. But let's see what this is going first. 0x15 CB. CB. Yeesh. And it calls 0x5B2. What's that? Is that the same one? So I don't know what we want R2 to be. But let's at least make sure we know how to mess with it. So case, this Synacor instruction is annoying me. So Synacor.inst. Actually, do we ever use raw opcodes? We don't ever use raw opcodes here anymore. So the place where we're doing import opcode.star, we can replace that with import inst.star. And then all of this Synacor.inst we can replace with nothing. So much easier to read. You're so close. Okay, the function where we want to insert code is here. No. 178b, call. Okay, so case, call, and we want a specific value, 0x00, oh no, 178b, 0x178b dot address. Well, that is, we need an arg, right? We need to pass an arg in. So let's do arg dot from word a. No, that. Okay, so if we find that literal value, then we have this bit so equal R2. So we want this to be true. So we don't want the jump false here. So we're going to skip ahead. First, we're going to set R1 to 6, and then we're going to skip ahead. So this dot store reg dot R1 6.toLit. Yeah. And then we progress dot no output. Well, thank you for the comment, ChatGPT. How does No, sometimes I don't know. But yeah, there's no call. There's no jump. What is the phase for? Oh, good question. Um, so I wanted this to be well formed. So if you'll notice my instructions here, most of the time they're doing a certain value, right? So first they update the memory or the registers or whatever. So they do a bunch of updates, and then they move the instruction pointer, and then they wrap output or handle input or whatever, right? So there's always these three phases. So I wanted to make sure that a tick went through all these phases. So some of these functions I can't call unless we're first in the ready phase, right? So say like store. I can only store if we are ready to execute an instruction. Whoops. Where is that? Yeah, so using is ready. So I need evidence that our state, our current state, is in the ready phase, right? And after that, we we end up in the updated state. So we can't do a store anymore in this state, right? Um, but we can move. So if we can move, our state has to be either ready or updated. So it just simply won't compile, right? If I were to write the code, just this dot no output, then that would fail to compile. That's a compilation error. So it enforces that we go through all that state. So in particular, I had this bug I wrote early on. So I would have like no output. I would forget to move the instruction pointer, right? But since since there's a requirement here that we've moved, I can't write dot no output unless I have first moved the instruction pointer, which is pretty cool. It's a compilation error. So that never it's literally impossible for that to be a runtime error. Um, unless I do like some weird hack. But all my weird hacks, all these hacks here, these require permission. All these combinators here, all these state transition functions, they are all lawful, right? But if I were to just modify the PC, then I need permission. So I need this emulator.hackperm in order to do any random other modification. It is pretty neat. Thank you. But anyway, I'm stalling again. Let's do this. So we're gonna run Synacor.main. We have compilation errors. Play. No, those are just warnings. No. We have compilation errors somewhere. Case instruction play. Syntax error in play Scala 93. We're not even using that file. What did we do? Oh, right. We'd started making another version of our function. We don't need to do that. Okay. Let's go back to compiling. Call arg.fromWord ambiguous given instances. Oh, yes, we need to give it a type. Call dot, wait, where is that? NVM state here. We need to say that this is an address. Address cannot be used as an extractor pattern. Yes, we need this whole thing to be a literal value. So we wrap it in the backticks here. Normally, if it's like obviously a literal value, just like this, that'd be fine. But since these are words, that can actually be an extractor function. So all of these here are extractor functions. You can define your own if you want, but these come for free when you define a case class for the pattern matching. Um, okay, for fuck's sake, let's just give it um okay, val Ackerman address ack address equals what is it? 0x. Wait, did we pull it out? No, it's in here. 178b. Arg address dot value. Okay, so this is to word. Yeah, dot to word dot arg dot value. Is that right? Is that compiling? Okay, now we go here and I'll just put in the ACK address. So if you find the ACK address, oh, but hold on, that's going to be, I still need backticks because that could be interpreted as is backticks the right thing? We need that? No, I think it's backticks. Okay, cool. To word is now member int. Did I mean, what did I mean? Members package. What's our conversion function? On int. Oh, okay. Oh, let's just do to address. Dir. I forgot my own API. To address. Okay. Okay, we're at the ruins. Before we use a teleporter, we can set the values. Let's set the value of R8. So set R8 to 42. That is the answer, right? And then now we use teleporter. Oh, wait. Uplog toggle. So now it's enabled. And now we can use teleporter. Sorry for the tiny screen. Here we go. Okay. That stuff happens, and it is hopefully not an infinite loop. It's looking kind of infinite to me. It's looking unfortunately infinite. Okay, what's being called? Call 178b is still being called. Yep. I do think I want a print line here. Oh no, it's stuttering. VS Code is lagging here. Is this still running? It's not running, right? Can you show set, please? What do you mean? Oh, sure, the implementation is set. I'm sure that is probably fine. I suppose I could verify. Yeah, I'm gonna pull set on screen and I'm gonna go to the bathroom. So if you see a bug, you can do that. And what else will we need for that? VM state. def updated inside of registers, and you'll also want to see these. I think that's everything you need to see the implementation is set. So we can debug that. Okay, be right back. Oh, yes, you are right. Okay. Oh, Liquid Quake, hello, welcome. Base 19. Oh my god, my base is wrong. So let's just run through what happened again. Or not through the whole thing. So let's set R8 to 42 to value 2A. That's correct. Yeah, it is 2A. Oh, I see, I see. The text might have been like small on my screen. So I think that's right. Get R8. Cool. And as long as we're not like off by 1 or something. In fact, let's just get all of them. Let's get like R1. Yeah. Dang, now I wish I could get all the values so I could prove that they're there in order. But that's what we had the worksheets for, right? So we could like verify in there when we set it. But now the thing I'm worried about. Oh, hello. You learned about the existence of the Ackermann function from union find, which requires mutation to get its inverse Ackermann big O of time complexity. Oh, okay. Interesting. Inverse Ackermann time complexity sounds amazing. Okay. So we have our hacks. Where is it? In VM state. Yeah, let's just do it again without running the op log. And then we should see this print pretty soon, yeah? So this dot store R1, the value 6. And we are doing that because in Scratch 2, um, where is it here? R1 equals R6. Yeah, and then we're skipping this function. So we just set R1 to R6 to skip the Ackermann function. And now since this should be true, it will jump a false. So now we do this push R1, push R2, push R3, do all this stuff. Then we call this function, which might be hurdle number 2. It gets called several times, actually. It's actually just... That number does sound familiar. 0x 5b2. Is that our XOR? Wait, no. 0x0 5b b2. Whoops. Yeah, it's one of the functions that we call. We have not deciphered it yet, but it is called a few times. And if it is recursive, call R6 Jesus. Call the value in R6. Where does R6 get set? R6 gets set to R2. R2. So R2 is an address parameter to 0x5b2. No. We set R2 to 0. We set R2 to 0. Then we add 1. So R2 is 1. Jump true 1 to this 5c8. Okay, so we have more busy work in this 0x5b2 function. I'm gonna mark that too. So if we have 0x05b2 dot to address, is that how we do it? Yeah, to address. Then we're gonna print line 0x05b2. We're not enabling any hacks. Called. And then we're gonna do just the normal call function. So we're gonna push yada yada, and then jump to 0x05. So we'll do a at that. Okay. Cool. Let's get out of here and run again. Print in. We got print line. Not found. It's expecting that to be a literal. Right, so we actually have to give that a name. Now, ideally, I could just write that, like a normal literal. But this is parsed as an int, right? But now there is something in Scala. It's an experimental feature. It's called numeric literals. And so like all of this comes from like a string parsing method, right? So you implement a string parsing method for your numeric type. And if it can parse successfully, then that works, right? So then if I made my own address, or if I made my own like numeric literal for the address, I could do like ADR equals that, and I wouldn't have to write this to address. it would just instantly parse that as like a literal address. So that's what I would like to do for this. But I guess I can't. So we'll just name this val address 05b2, I guess. And then we put the literal in here or the function reference. So address 05b2. And then we're going to jump to 05b2. Can I get a pattern guard? Did you define a toLit? Is that appropriate here? I have a to address. Oh, I have a toLit and a to address, but here to address is what we need. Wait, why is it not defined? Can't I use a pattern guard? This is a pattern guard. Oh, wait. You mean like an if? Yeah, okay. Totally. I can just do if A equals. Yes, totally. Oh my God, you can tell it's late at night. Okay, so we can just do A if A equals 0x05b2 dot address. Okay. Good catch, Macaw. Oh my God. And honestly, let's do the same thing here. A if A equals 0x. Come on, Copilot, you can do this. Tell me. It's right here. And we can just pass in A here. Cool. Case call A if, no, if A equals that. Value address is not a member of int, but A should, oh, hold on, A is actually, let me jump to the definition of call. Inst A, it's not an address. Call, it's an arg of address. And an arg is either a constant, so it means arg.constant address. There we go. Right, so that wouldn't have worked either. So 0, what is it here? Oh, you know what? That's probably what happened. Is it never actually called because it wasn't compiling because that was incorrect. I could also destructure this by saying like arg.const in here with A with an address. We'll just do A. What's the advantage of that just versus just putting it inside call? Well, I can't just put it inside of call because I can't put the address in there. And my addresses aren't real literals. Hold on, it's to address. Let me fix that real quick. To line jump, there's no A. Required address. push to jump A. Oh, wait, we need to do here an A dot value. A dot value. Oh, that happened a lot before we even got there. Okay, so it's just a common function then. Probably used during output. Okay, so set R8 equals to 42. Use teleporter. Hex enabled. There we go. Look at that. Look at that. This is probably not a valid code, but let's read it. Let's read it. A strange electronic voice is projected into your mind. Unusual setting detected. Starting confirmation process. Estimated time to seek to completion is 1 billion years. You wake up on a sandy beach with a slight headache. The last thing you remember is activating that teleporter, but now you can't find it anywhere in your pack. Someone seems to have drawn a message in the sand here. It begins to rain. The message washes away. You take a deep breath and feel firmly grounded in reality as the effects of the teleportation wear off. This is a sandy beach in a cove on some tropical island. It is raining. The ocean is to your south and heavy foliage is to your north. The beach extends west and east. There are 3 exits here. Oh my god. Yeah, let's validate that code. I have a feeling MD5 sum. There we go. And let's check that. 313 ending in 64. 313 ending in 64. It is a bogus code. It is a bogus code. But hey. So we don't need this. Let's comment that out. But this is skipping Ackerman. Hackerman function? Yes, this is exactly the Hackerman. That is the name of our little exploit. So that skips the verification process, but what happens after that is what I want to know. And can we figure out the next part, or must we? So we bypassed it. Now we just need to like set it to the right value, right? So this is what gets called after. And then where does R8 get used again? Well, we call that. So R8 is checked here. R8. The function from the infinite loop. Yes. Wait a second. Where all is this used? Okay, there. There. Set R1 to the value in R8. So the first check is that it's non-zero, and it does all this thing. Then we set R1 to the value of R8. Set R2 to that value, set R3 to that value, yada, yada, yada. And then we call this. So I think we need to know what's in this function here. Well, it's called in 2 different places. Maybe that's not what we care about. But I do still want to see what it looks like, yeah? So in our play.scala, 0x731. 0x 0731. I don't know how many returns we'll need. Let's default to 0 for now. Okay. Before we get there, what does a strange book say? Good question. You know what? Let's pull that up. It should at the very least allow you to determine the value of the 8th register. So yeah, we need to optimize it to determine the value of the 8th register, which would have been accepted by the teleporter's confirmation machine. Then we set the 8th register to this value and activate the teleporter to bypass the confirmation mechanism. Yeah. So if the 8th register is set correctly, no anomaly should be experienced, but beware, if set incorrectly, the now bypass confirmation mechanism will not protect you. Okay, I'm gonna pass this along to chat so that you can all read it. And you know what? Let's get YouTube in there too. Alrighty. Before we do any of that, let's look at this beach. Okay, so this is a sandy beach in a cove on a tropical island. It is raining. The ocean is to your south, heavy foliage is to your north, and the beach extends west and east. Well, should we go straight into the forest? I think so. Nah, let's explore the beach. Go west. Oh, let's check our inventory. We still have a lit lantern. Oh boy. 0x5b2 is going to get pretty annoying. Let's redo this. So I removed that. I removed that call. Set R8 to 42. Use teleporter. Ackerman enabled. Yes. Okay, let's go west. This is a sandy beach in a cove on some tropical island. West is an embankment of the cove, which looks too steep. Ends to the east, and there's dense foliage to the north, which seems uninviting. Am I missing letters here? Ends to the east, and there's dense. Okay, well, let's go east. So we're back at the beach. Go east some more. This is a sandy beach in a cove on some tropical island. It's steep cove and back. Yeah, we're missing letters. Let's look again. Ah, yes. Here we go. I think we need to be even smaller. It is raining. There we go. That looks better. It is raining. Nope. Even smaller. Okay. It is raining. The steep cove embankment to your east blocks your path, and the ocean waters here look unsafe. The beach extends to the west, and there's dense foliage to the north. So let's go west twice again, because I want to read that thing we missed. This is a sandy beach in a cove on some tropical island. It's the same thing. It is raining. To the west is an embankment of the cove, which looks too steep to climb. The beach extends each. Okay. Well, I think it is time then to go north into the foliage. Large trees here seem to be protecting you from the rain. As you push through the undergrowth, you can hear birds chirping overhead. There's a steep rock S. I feel like we're missing letters there. to your west, blocking your path. Oh, there's a steep rock face. I see. To your west, blocking your path. Um, let's go north further. The embankment of the cove comes together here to your east and west. Between the tall trees, there's a narrow, overgrown path leading north. You hear waves lapping up on a beach through the dense vegetation to your south. Okay, let's go on that narrow, overgrown path. You're on a narrow path between two steep rock faces which look like they have been here for thousands of years. Rain trickles down through the vegetation and moss, and through the leaves you can occasionally see a sliver of light hundreds of feet above you where the rock walls end. Okay, let's keep going north. The narrow path slopes downward to the north and leads to the mouth of a small cave. A sign reads Treasure Vault Access, but different handwriting has crossed out and written Lair of Horrible Monster. All non-pirates keep out. uh, well, we have no choice, right? We have to go into the Lair of Horrible Monster. I think there's a branch back here we could have gone east. But we do have an undo function. So if we get eaten, we can always undo. North. We stand at the entrance to a natural cave which looks like it hasn't been visited in quite some time. Light pours in through the opening to the south, while fireflies light the path further into the cave to the north. Further into the cave it is. Fireflies slowly drift around you and light the tunnel, which seems to get brighter to the south, but dimmer to the north. North. The cave is a little wider here. You find the cobweb-encrusted remains of a small camp, and although you don't suspect the broken pieces of tables and chairs will provide useful to your quest, the fireflies seem to like using the debris as a shelter. A passageway leads north and south, and there's an alcove to the east. Um, why don't we take a detour through that alcove? So let's go east. At the back of this alcove, there's a small table, a chair, and a broken lantern. It looks like this space was used more recently than the camp to the west. Things of interest here. There's a journal. Take journal. Look at journal. Fireflies were using the dusty old journal as a resting spot until you scared them off. It reads, Day 1. You know what? So we still have more work. I think this might be a place for a cliffhanger. It is 5 a.m. I've been at this too long. But I think for sure tomorrow night, all we have to do is figure in the correct input to the Ackermann function, right? I'm sure like R8 is checked elsewhere. um, of course, you can cheat and you can read this. It's on my screen. But yeah, I think all we need to do is figure out the correct input to the Ackermann function so that that 6 comes out. Um, then we don't have to skip it. I mean, we'll still skip it. But yeah, that's the last puzzle. And of course, we have to explore this weird stuff, right? You didn't realize it was 5? Yes, it's 5 a.m. on the East Coast. But hey, this is huge progress. Let's write our own journal entry. So wait, not this. This. Yes, new area unlocked. So what is today? 2025, 12:23. Part 7, bypassing the safety mechanism. What exactly is it called? Confirmation mechanism. Bypassing the confirmation mechanism. So we have bypassed that. So added proper instruction modeling, added method for extracting functions, found Ackermann function being called, bypassed Ackermann, found new area, and found a journal. Okay, that's good progress. So yeah, I think at this point tomorrow is the finale of the series then. So thanks to all of you for stopping by. We've got a good set of regulars here. So Zuno, of course, and Bob, Ice Cold Witch. Who am I missing? Macaw comes in. Liquid Cake is good to see you for a bit. Have a good night, all of you. And what am I missing here? It is a this it is a very cool challenge. Yes, we can all sleep. We can all sleep. Um, and we can all have a satisfying finale tomorrow. Hopefully, hopefully. Um, let me find a stream to raid. You didn't expect it to be fun, knowing that Eric wrote it? Good night, Ka. So Twitch. Having a code, my usual. Let me turn off my music. And we will find a stream to raid. Let's set it to recommended for me. Yes, Oding is on. Must be early. It is immersive. Still developing Stardust. I don't really recognize these people. Is anyone doing anything to do with assembly? Because that's sort of what our theme is right now, right? Nope. Emulators. RTS and Godot. What do you mean so fun? I don't get the scare quotes there. Oh my god, all the Europeans are awake. It's so late at night. Yeah, it is interesting to see how the people approach it. I hope Dave Eddy gets back on because I want to see. Tonight was especially fun. I think tonight was like a highlight night for me. Okay, I'm gonna start clicking on people here. Someone's doing stuff in Godot. Do we have anyone doing any kind of functional programming? We've got a lot of Unity. See, I'm not much of a real game dev myself. Ask game dev questions. I don't want to jump to TS Oding just because that's such a big stream already. Unfortunately, no one here is someone I'm actually following. Okay, we are doing something game related. We're like reverse engineering a game. So maybe we can do this. Let's do a quick vibe check. RTS in Godot. There's some battle going on. Oh, let me see. Oh, building a bad text adventure game. Here, perfect. Okay, we've been doing text adventures. And here's a text adventure. Okay, we found it. Uh-huh. So let's raid sine wave mood. Oh, I was the 50th follower. Great. Okay, let's make him even happier. Okay, good night, everyone. Thanks for the stream.